Hello. We're going to continue on with our uh, study of things that are going to help us with our civil engineering and truss uh, project and just kind of understanding how that all works. And the next step of that is looking back again at moments. This is another one of those things that we talked about in the fall. So we're just going to do a little bit of highlights of this. We're not going to do everything. So if you look back in the fall and you go back and find this PowerPoint, this is just going to be a part of that, not the whole thing. I just want to go back over some of the highlights of it and talk about how it fits into what we will be doing with bridge trusses. All right, so just a quick reminder of what a moment is. A moment is just a measure of a force's tendency to rotate a body. So when we look at something that's going to cause rotation around a point, that might be something like a wrench, or you look at a teeter totter out of a playground, something like that. Anything that's going to cause you to rotate around a point is a moment. And so we look at the force, and we also need to look at the distance that is applied at to calculate the moment. And so here's an example of kind of how that works. So if you're turning a wrench, you're applying a moment to that bolt by turning it with that force causing that rotational motion. All right, so here's another, hopefully a little closer look. So we do have a force that we're going to be looking at. That is part of what causes that moment. And then we also need to look at then is the distance from the pivot point, that center point that we're rotating around, out to where that force is applied. And again, that's a perpendicular distance. So we want to know how far is it from here to here at a right angle to that force. So whatever that force angle is, we want to know the distance perpendicular to that force. And then what we'll find then is that the moment is going to be the distance, that distance from the pivot out to where the force acts, which is our lever arm or a moment arm, times the force we're applying. And so if we increase the force, obviously we'll get more moment, but also if we increase that distance, we'll get more moment. And so those are two different ways that we can adjust the moment caused, that rotational force that we're causing, is by adjusting how much force we apply, but also by changing the distance. And if you've ever tried to, get something like a bolt that's stuck and you want to turn it and get it moving, especially if you're like changing a tire, that's usually a pretty common place that you run into that. One of the ways that you can do that, of course, is to apply more force. But sometimes if you can't apply more force, the second option then would just be to increase the length of that lever arm. And so you get like a piece of pipe or something like that to put over your wrench and just increase your moment, your torque. And moment and torque are very similar in their terminology. So you can call it that as well. Unit wise, we are going to be looking at two different options. Project Lead the Way likes to use the English unit, so you're going to see foot pounds. They put pound force first, but usually we say foot pounds. It just sounds better that way. Or you say Newton meters. This would be what you're going to get when you get into physics. Everything's going to be in Newton meters. But again, in Project Lead the Way stuff, we'll say foot pounds. And just a quick reminder again, rotational directions, that counterclockwise and clockwise are the two ways we're going to be looking at. Counterclockwise is positive, and that's just like we do in math when we start looking at rotation in math. Counterclockwise is always positive. And if you look at the quadrants on a coordinate axes, we always label them. The quadrants is 1, 2, 3, 4, going from the top right and then going counterclockwise around to the bottom right. And then clockwise will be negative. So just keep that in mind as we go through this. You need to think about which way is the motion going to go. Is it going to go clockwise or counterclockwise? And we talked about the right-hand rule, which I'm not going to go over again. But realistically, just think about, if I were to actually rotate that thing, if that force was going to allow that to actually turn, which way would it go, clockwise or counterclockwise? And that's how you're going to determine whether it's a positive or negative value. That's what we need to think about. All right, so when we start looking at bridge trusses and looking at this part of civil engineering, what we really want to think about is equilibrium. We've talked about this before, and primarily we're looking at static equilibrium. What happens when we get things in balance? And equilibrium is kind of a balance point. So we say something is in equilibrium if it meets one of these two conditions. One of those is that it's not rotating, again, sitting still. The other option, which we're not going to run into, and it's not a real common one, but it is possible, is that you have an object that's spinning at a constant speed. And I'd say it's not very common because it's just really difficult to meet that condition for most things. You're going to get some sort of acceleration, some sort of force acting on it that is outside of um, the normal. So you're going to get something that's not going to stay constant speed all the time. I mean, like I said, it's possible, but it's just not as likely for us to run into that. So more often than not, we're looking at things that are not rotating. And so if that's the case, if either of these things are the case, we are in what's called rotational equilibrium, or really just static equilibrium is what we're shooting towards, where everything is stopped and everything is sitting still. But the important part here is that if that is true, then all the moments on that have to add up to zero. There's no moment that is unbalanced that's causing it to move. So, everything's balanced out. It'd be like holding a teeter-totter still with somebody on one side and you on the other, and you're just holding it still. You're keeping things in balance. And so if that is the case, then we know that the sum of all the moments that are acting on that object should add up to zero. And so this is the formula we're going to use. And we have really three of those we're going to use, but this is one of them. And this is going to be the one we use maybe not very often, but certainly one of the first things we'll use is this sum of the moments. Okay, so quick review, kind of how does the moment problem work? So here's our teeter-totter. And so we know that if you put equal loads on either side, that it should be in equilibrium. Now, it's difficult to get that balance, but if you can do it, that we have the equal distance and equal forces on either side, that we will be in equilibrium. If we are not balanced, then we're going to see movement, and that movement is going to be that moment. Moment is not balanced, and it's going to cause it to rotate. Now, once you hit the ground, now the ground is applying a force, and so the ground is going to supplement the moment caused by the smaller bear and keep things balanced again. So it's still, at this point, once it hits the ground, it is back in equilibrium, but it's not going to be equilibrium where it's just the two. Now we actually have a third force, which is the ground pushing back up. So if we wanted it to be in equilibrium, what we'd have to do is we'd have to make sure that the moments are the same. And so we'd look at the forces of the two objects, which are these two bears. And we also need to look at what are those distances, those lever arms that we have. And so if they tell us this one is 4 feet away and we know the force is 25 pounds, we can calculate the moment caused by that bear. And so you multiply the force times the distance, and then we look and say, okay, well, is that clockwise or counterclockwise? This one would be counterclockwise because if you allowed it to rotate, it would go down and around in a counterclockwise rotation. So that's going to be a positive moment, and it's going to be 25 times 4, so 100 foot-pounds of moment. If we take the other bear, which is 40 pounds, what we want to look at is how far away would that need to be for it to be in balance. And so that's where we did way back at the beginning of the year, and we did simple machines and we looked at levers. We basically did these calculations. We were looking at, what would that distance need to be? Now, we weren't looking at it from a moment calculation perspective. We were talking about it as a simple machine and levers, and we had our rules for levers. But really, the rules for levers are moment calculations, because we're going to say is the moment caused by this force should be equal to the moment caused by this force, but opposite direction. So for those to balance, for them to be in equilibrium, the moment caused by this and the moment caused by this should be equal and opposite. They should cancel each other out. And so to do that, then we go ahead and say, okay, well, our two moments, we know they're going to add to zero if this is an equilibrium, which is what we're assuming. Then the moment here, moment for 1 plus the moment of 2 should add to zero. The second force is going to cause a clockwise rotation, so it's going to be negative. So this one's actually going to be a negative value. And so we can say then is moment 1 is equal to the negative of moment 2, but moment 2 is negative. So this equation as a whole will end up being where a positive equals a positive. But we'll get into that here in a second. So what we're going to do then is just say, okay, well, since I know that that's going to be the case, this is going to be a positive value because it's negative, I can just go ahead and plug in my calculations. So my moment calculation for 1 was the distance times the force my moment calculation for 2 is the distance times the force, the moment arm times the force. And I don't know that distance, so that's what I'm solving for. So I'm going to plug in what I know, which is 3 of those 4 things. I know the distance 1 and force 1, and I know force 2. I'm looking for distance 2. So I'll get 25 times 4 is 100. And then they, for some reason, switch back up to this format up here where they're adding them together. That's fine, but I don't know why they do it this way and then switch it. But realistically, what we're saying is going to equal to 40 times d2. So 25 times 4 is going to equal 40 times d2. And so we get 100 equals 40 times d2. We'll divide both sides by 40, and we'll find that 100 divided by 40 is 10 over 4, which is 5 over 2. And so that's 2.5. So 2.5 feet away. So for us to be in equilibrium, we would want that to be 2.5 feet away. Now, again, equilibrium would be balanced, so that would mean that this would stay still at that point. We're holding it in equilibrium. Okay, so let's put this into context of what we'll be doing with actual civil engineering and looking at bridge trusses. We look at a bridge truss. This is about as simple a bridge truss as we can get, which is going to be just a single supported beam. And so on this beam, we have supports at both ends, and then we're going to have a force that we're going to add on here in just a second. There we go. There's our force, which is going to be that present. And what we want to know is what is the moment caused by the present on there. Really what we really be looking for, not so much the moment, what we're really looking for is what are the forces at A and B, because forces at A and B are going to be our starting point for every bridge truss problem. These are our reaction forces. These are basically the supports. We want to know how much force is being supported here at A, and then how much force are we holding up here at B. And they're not going to necessarily be the same because we're not setting this in the center. If we'd set that in the center, then A and B would be equal because we'd be equally dividing that weight. But here you can see that C is a little bit closer to A, so we're going to have a little more force on A than we do B. It's not going to be evenly distributed, but what we don't know is what those forces are. So we're going to use moments to help us figure that out. And so to do that, we're going to look at the force. So in this case, it's 35 pounds. And so now what we want to do is we want to set up a little free body diagram. And so we're going to draw on the forces of our two supports. So we have a reaction force at A, which is in the y direction. It's holding up this beam. And then at B, we also have a force that's holding up the other end. And so we want to look at is what is the distribution of that 35 pounds between these two forces. And the way we'll do that again is we're going to use moments. So we'll pick an end. I think in this case we're going to pick A, but really you could pick point B as well. But what we're going to do is we're going to pick one of these two endpoints and talk about that as being our pivot point. Now, is it really going to move? No. But we're picking out a point to serve as our pivot for our moment calculation. And we always want to be judicious in this pick. We want to pick out one that makes sense. We want to pick it so that one of our forces is not going to cause a moment. And the only way you can not cause a moment is to have either no force, which is not going to be the case, or we want that moment arm, that distance from the pivot point out to where the force is acting, to be 0. And so we always want to pick our moment pivot point to be where one of these unknown forces is acting. So that's why we're going to pick either A or we're going to pick B. If we pick C, we'd have two unknown forces causing moments, and that really wouldn't help us. So we're going to pick either A or B as our point. And again, in this example, they're going to use A. So we're selecting A as our pivot point. So what we want to do is think about, okay, well, what would be the moment caused by this force over here at B? We know that A is not going to cause a moment because its distance from A to that force is 0. It's going through the point, so there's no distance, so there's no moment caused by A. But B is going to cause a moment, and the distance between A and B is 10 feet. And so we know the moment caused by RBY, that reaction force at B, is going to be the force times 10. And so we're going to have that. The other thing we know is that C here is also going to be causing a moment. It's applying a force at a distance. In this case, the distance is 3 feet. And so we have 35 times 3. So we have enough information to set up a moment equation. Now, they're not on opposite sides of the pivot point, which is okay. This goes back to our levers. If we had the forces on the opposite side of the pivot point, it was the first class lever. Here it's going to be either a second or third class lever, depending on your viewpoint on it. But it's okay that both the forces are on the same side of that pivot point. All right, so we're going to say the moment caused by B plus the moment caused by C have to add to 0. And then we want to think about, okay, which one of these is positive? And so B would cause it to go counterclockwise. So B is our positive one. C is going to cause a clockwise rotation, so it's our negative one. And so again, it would be MB minus MC equals 0 if we throw in the direction. They're not doing that yet. They're just doing the math as if we didn't know that. But we know MC is going to be negative, so that's going to make this end up being MB is equal to MC, because negative of a negative is going to be positive. Okay, so we know that those two moments should be equal. And so we'll plug in what we know. We know our distance AB. We don't know RBY. We know our distance from A to C. We know our force at C. So we can plug in all those numbers. So we have 10 times RBY equals 3 times 35. And that's the moment caused by this present here at C. And you'll get your value, which is going to be 105. And then take 105 divided by 10, because we're going to divide both sides by 10 to solve for RBY. And see, okay, well, 105 divided by 10 is going to be 10.5. So that's telling us that the amount of force that is being held up here at this end is 10.5 pounds. So 10.5 pounds of force is being applied to this beam at point B. That means that point A is the rest. So if we take 35 minus 10.5, you're going to get 24.5. That's the force at A. So as we know that RAY plus RBY have to add up to 35, otherwise this beam would be moving. And so since it's not moving, we're in static equilibrium, we're not moving, then RAY plus RBY, those two forces in the Y plus this force have to add up to 0. And so in this case, RAY plus RBY have to equal to 35. And so we know that the difference between the two would be 24.5. So we're getting 24.5 pounds of force at A, we're getting 10.5 at B. Those two will offset the weight of your present that you're setting on there. One note that we might point out here is we're assuming this beam has no weight, which is not a good assumption, but it's the assumption we're going to go with through most of the stuff. What we're really assuming is that the weight of the beam is negligible compared to the force we're putting on it. Again, that's not actually a good assumption, but it just simplifies the problem for us quite a bit. Okay, this is a little bit more realistic of what you're going to see. So this is a very simple bridge truss. So you've got 1, 2, 3, 4, and 5 different beams that are holding up this bridge, and it is supported at points A and D. And what we want to know is how much force is there at A and how much force is there at D if we apply a force to this truss. So here they're saying I've got 600 pounds pulling down right here at point C. How much force of that 600 is being split between A and D? So if we look at the moment, and then we also add another force in here. So now we've got two forces acting on this. Same principle though. We're still looking at how much force is at A and how much force is at D. We're just going to look at how much moment is being caused by these two forces. Okay, so we're going to replace these two endpoints here. We'll talk about this a little bit more later about what this force is and the difference between these types of joints. Let me go back real quick. This is what they call a pin joint, and pin joint means it's holding it in place. It allows for rotation, but it does not allow for XY movement. So it's basically like you stuck a bolt through a hole, and so it's allowing it to rotate around that point, but it will not let it move. Whereas at point D is called a roller joint. So you can see the little circles there that represent a roller. What point D is almost like if I have it setting on top of a wheel or something, where it keeps it from falling, but it would allow it to move horizontally if it could. And again, it's not going to do that. But the reason why you have a roller joint in a bridge structure like that is because as the temperature changes, that metal and the beams are going to expand and contract a little bit. But if you don't allow for that expansion, if you don't let that roll and move horizontally, you're going to actually break your bridge, and that's a bad thing. So they have that ability for one end of this to move a little bit for that reason. So anytime we draw these out, we're definitely going to want to include a pin joint on one end and a roller joint on the other. Okay, so we're going to again replace our two joints. This one is preventing motion in the X and Y, so we're going to have a reaction force in the X and Y. Here, this one only is holding it up. It's not keeping it from moving in the X direction, so we don't have a X directional force there. So we do that. So this is kind of a start for a problem that we would be doing. And we'll talk about this more in the actual bridge stress video. But this would be our starting point, and we'd have all this free body diagram drawn out showing all the forces acting on our bridge. And then we want to start by finding the forces at A and D. And so we're going to look and say, okay, well, let's pick A. Again, we pick one of the endpoints where we know a force is acting, because that would allow us then to basically get rid of any forces that act through that point in our equation. Because again, it's the force times the distance. If the distance is 0, so if it's going through the point that your pivot point is, your distance is 0, you will have no moment caused by those. So RAX and RAY are not going to cause moment around point A if we use point A as our pivot point. So that's what we're going to choose. What we want to use that for then is to try to figure out what is RDY. So we have one unknown once we use A as our pivot point, because those two, again, won't cause a moment. So we're going to try to solve for RDY using our moment calculations. And so I actually have three forces. I have the force at B, the force at C, and the force at D that I'm dealing with. But I know these values. I know what its force is. I know the distance from A to each of those. What I don't know is the force here. So that gives me one unknown for this moment calculation. So I'm going to add the moment for C, the moment for B, and the moment for D all together. And they've already kind of started off here by figuring out the direction for us. If we look at D, D is going to cause a counterclockwise rotation. It's going to push us up and around this way. So that's a positive moment. These two would cause it to rotate clockwise. So if I were to hold this still and I push it this way, it's going to want to go around clockwise. Same for the one at C. It's going to want to go clockwise. So those are both negative. Again, putting in the positive negative based on the direction. We don't know what the values are, but we know they're positive negative based off of that. And so we know that MD should equal MB plus MC. So we're adding those together. So if I can figure out the moments for those two, the moment should equal the moment for D. And so we can find that value. The distance for B is going to be 12 feet, because again, it's perpendicular to the motion of the force. So the force is going horizontally. Then what the distance we want is from there to that direction of travel or direction of the force. So we want that distance at 12 feet. So for that one's going to be 12 times 500. This one's going to be 24 times 600. And so we'll get both of those moments in there. So we have moment for D is going to be that distance, which is 24 plus 8, so 32 feet, times RDY is going to equal DCB, which is 12, times F of B, which is 500, plus the force here and the distance here. So the distance is 24, the force is 600. So you get 32 times RDY equals 12 times 500 plus 24 times 600. Put it all in your calculator, find your value. And so we find 6,000 plus 14,400. So 20,400 divided by 32, because we're solving for RDY. And so RDY is going to be 640 pounds. So if we were to measure the amount of force this support is holding up, this support is holding up 640 pounds. Now, here's the question. What would be the force at RAY? Well, if this one's 640, what do we know? We know all the y directional forces. This is going back to our free body diagram stuff. For this to be in equilibrium, for this not to be moving, for it to be sitting still, all those y forces have to add up to 0. We'll talk about that some more. So if this one's 600 and this one's 640, what would A have to be? And it's kind of weird, but this is kind of an unusual case because of this force up here at B. We actually come up that RAY is actually going to have to be going the opposite direction. Like if you added all those forces together, RAY plus RDY should equal to FC. However, in this case, RAY plus RDY, you're going to get RAY plus 640 equals 600, which means RAY is actually negative. And what does that mean? Well, that just means that when I drew my picture, I assumed it was going up. But if I get a negative value, that means I drew it the wrong direction. And that's okay. It's not a big deal. That just means that I drew it going up, but it's actually going to be going down. So in this particular case, and it's really, again, it's because of B over here, RAY is actually going to be holding this bridge down instead of holding it up. RAY is actually keeping it from rotating around because it actually wants to pivot around point D, and RAY is actually keeping it still. So anyway, that's kind of what we're looking at. We're going to stop there, and then we'll come back and look at bridge stresses in our next video. Thank you.